All right. Welcome back. So last lecture was mostly about conceptually the kind of attacks that are possible. And there's a lot of research, machine learning security research, that has studied these attacks and how to make them more effective, how to search for adversarial examples, how to harden against prompt injection. Today I want to step back a little bit and think about if we want to build systems that are reasonably secure, how do we do that? We can try to make the models slightly more reliable and defend against some of these, but often you have more of a system angle to think about this. I want to stop by going back to think about what do we actually want with security. And we have quite different security concerns about who our attacker is. In traditional, or in a lot of security concerns, there's what we distinguish as a very targeted attack by a highly motivated, highly resourced actor, often a nation-state actor, like a secret service of some country, and they have a lot of resources and a lot of patience to attack a system. I think it's pretty clear that this was Israel, their secret government agencies trying to attack Iran several years ago by taking down a lot of centrifuges through an attack on their software systems. So they had a bunch of exploits, could get into those systems and essentially make these centrifuges blow up by getting them into an unsafe state where they were running too fast or something like this. This was very, very targeted at a very specific system with a lot of patience. They used zero-day exploits that they probably paid millions for, or that would have been worth millions on the black market. They had a blast radius where this was an exploit that then a lot of other people could use, but it was very targeted. These are extremely difficult to defend against. If you have a country trying to attack your system, good luck. You're going to be in a very difficult security space, but you probably also know that you're in a space where you have secrets that somebody might pay a lot of money to get into your system. A thing that we often care about, what's sometimes called a smash and grab attack. These are the kind of things where you may have configured your system incorrectly. This is actually something that typically happens to 2 or 3 teams a semester, that you install MongoDB without a database, and one morning you wake up and your database is encrypted and somebody wants 2 Bitcoins to get your data back. This was not a nation-state actor that tried to attack your system, right, and get specifically money from you because they know you have a lot of money and this is highly critical data, right? That's really worth something. This is...
Just so you know. I will make fun of you. He pretends he won't, but he will be in a second. But when it's from a place of love.
I mean, our sysadmins usually get kind of annoyed and ask me to remind you again and again to Redis is the other common one. Yeah. It will probably cause 2 or 3 days of downtime for your system. Like a CMU security might shout at you, like internet security people, that you need to block this port or something. This is a good time when it happens before you get exploited. Otherwise, you hopefully have a backup, or you collect a lot of training data again and train a model again. These are usually not very targeted attacks. There's a security vulnerability somewhere in your system. You haven't patched something that's a known vulnerability, and somebody exploits this. This is often causing a lot of damage. There's these cases like the hospital being attacked by a ransomware attack. This was not somebody directly targeting a hospital. This was just a hospital or a student team, like in the crosshairs, right? And this can cause some damage too. The defenses and what you're concerned about in those kind of cases is quite different. As a defender, you usually have a problem. The attacker only needs to be successful once. They only need to get into your system once, and then they can delete your data, encrypt it, or demand money. As a defender, you always have to be successful. Right? The attacker can try again. They can try 1,000 SSH passwords, and if one of them was weak and yours and you don't have two-factor authentication, they might be into the system. So in the security space, traditionally we often think of wanting guarantees. Right? We want something that we can prove will always work, or at least we know it's really, really hard. Like if you have a really strong encryption mechanism, we're pretty sure that you can't randomly guess this, right? And we're confident in this. Machine learning doesn't really give you any guarantees. And all the attacks that we talked about last time, there's not really anything that can guarantee that you won't be attacked. We talked about different strategies of how you can avoid evasion attacks, how you can reduce the chance of poisoning attacks, how you can reduce prompt injection, but you won't get any guarantees. Who of you here uses Face ID or something similar to unlock your phone? This uses machine learning. We saw last time examples of how you can fake with some pixels, some physical glasses, to pretend to be somebody else. Does this make you nervous? The attacker only needs to be successful once, and then they can get into your phone. So traditional security tends to have this notion of, we won't provide guarantees. In the second lecture, I showed you this SQL injection example where we have traditional static analysis techniques that kind of make sure that there's never any flow from an untrusted source into this query here. And we can analyze this, we can prove this. In SQL injection attacks, we can guarantee that they can't happen in systems if we just pay enough effort and use the right tools. And we've gotten pretty good at classic security in a lot of ways, like buffer overflows. We know how to avoid them. If you're still programming in a language where you can have buffer overflows in a way that you're not checking against them, it's kind of on you these days. Right? You could have used Rust and prevented this. You can have some operating system guarantees or some extra checks in C. That might slow down your code a little bit, but there's no reason we have buffer overflows anymore other than kind of sloppy practices. SQL injection, the same thing, right? We discovered common patterns like default passwords, and other than MongoDB, we don't really do that anymore, right? And so 0 days, 0-click remote code execution vulnerabilities are pretty rare these days. And that's why this costs several millions on the black market, because they are so rare. And for attacks, modern attacks, you often need 2 or 3 of them together. So we traditionally want guarantees. And machine learning is kind of in a weird space where we can never get guarantees. We don't even know what a guarantee would look like for the most part, right? How do you guarantee that a face recognition model will only detect you and can't be exploited with some weird glasses? Somebody can change a few pixels to get into your phone. Yet we're still using machine learning in a lot of places where they're security relevant. Face ID is one example. Why do you still trust Face ID even though it's potentially attackable by adversarial examples?
It's convenient.
It's convenient, okay. And you probably don't have something on your phone that a nation-state actor really would be after. Although you may have some banking information. I don't know how hard it is with Face ID to submit money to myself if I could get into your phone, right? I need physical access to the phone first, yeah. Chocolate? I may not have that.
There's a second email that asks for my passcode.
Isn't the point that you don't need the passcode?
In case it detects that there's something suspicious going on.
All right. So what's suspicious?
If there's a suspicious attempt
Okay.
where it was not as confident, it generally asks for a passcode, or there are apps which are protected by a passcode, even if somebody can unlock it.
Okay.
Yeah, I would basically kind of say the same. So if you have applications like your bank account access, you wouldn't use face recognition there. You would have like a whereas for the phone only,
Okay.
I think that's what you meant by the second layer.
Yeah, I think it's the fingerprint for me for most banking things. Like that's the security mechanism. But maybe that's a larger point here. We don't always need guarantees. We have other mechanisms. So this is often kind of the Swiss cheese model of security, where we have multiple defense mechanisms that each may have some holes. But if one lets an attack through, another one would detect it. So most attacks are not instantaneous. People try to get into a system. They might get access to your system, but then they might look around in your system, and then some intrusion detection system could detect them. Often you don't have arbitrary many attempts. So when it comes to Face ID, I can't try 1,000 times and learn the gradients of the face recognition model to figure out which pixels I need to change. Right? That's the traditional way of how you do evasion attacks, that you may need many, many different attempts. And if I can make these attempts expensive enough, or I think Face ID, you may have 5 attempts, I don't know how many, and then you need a passcode. That might be good enough in most cases. It's not a guarantee, right? If an attacker knows the model weights for some reason and can construct this offline and test this in some way, they could get in on the first attempt. But I think it's pretty good in general. The whole point here that I'm trying to make is we won't get guarantees, but if we layer defenses enough, if we think about increasing reliability sufficiently, we might get to a point that the risk is low enough that we accept it. There is some residual risk involved. But that's true of almost everything. Like the guarantees happen for things like buffer overflows, SQL injection at a very low level. In practice, almost everything, there's some risk involved. And what we want to do is typically reduce the risk to a level where we feel this is kind of reasonable. So in the end, it's all about risk. Right? So what's the chance of a successful attack? It's pretty low, probably in the iPhone case. What are the harms from an attack? Depends on what you use your iPhone for. Can be really high, and maybe if it's really high, the potential harm, then you're not willing to accept a low risk of kind of coming in. What are the cost of mitigations? Like what are the security mechanisms that we can build in? Can we accept it? And now we can think about lots of cases, not necessarily security. This blends into safety. Claire will talk about safety on Wednesday too. What risks are we willing to accept? Have you seen this case? It's like a week old, I think. Some face recognition system accused somebody in Tennessee, some grandmother, of being part of a bank heist in North Dakota. She was never in North Dakota, at least that's what she claims. Was jailed for half a year and is now considered innocent. Model mistake, oops. Is this something we are comfortable with? Is this a risk we're willing to accept? I mean, you also have to consider what's the alternative, right? A human could have probably made the same mistake. Is the chance that this is happening lower or higher than a human? I think it's like we can't expect perfection of these systems, or we won't get perfection. But I think we can think about what safeguards are necessary that we can deploy them. And are we never going to deploy anything like this, even though it may have some benefits? If there's ever a chance of a false outcome. Right? Another example, again, image detection mechanism, right? You probably have seen this one. Have you? So this is OpenClaw starting to delete emails and not listening to, please stop doing that. Right, until the person actually had to unplug power. Like, this is something we can't fundamentally prevent, the way that these systems are designed. They can make mistakes. This is actually not an attack. It's, again, more of a safety thing. Are we willing to accept that? And right now, the prevailing attitude when it comes to machine learning is pretty much the thing on the left here. Figure out security. Stop being risk averse. Right? When it comes to AI coding, there's a very high risk appetite, I think, these days. And this is from the same people who made substantial mistakes of leaking their OpenAI credits and losing a lot of money. The right picture is actually before the left one. Right? It's the same people who are still saying, stop being risk averse. Maybe if you have millions of money in startup funds, maybe it doesn't matter, right? You want to be fast. Maybe that's fine to be stop being risk averse. So in the end, I think the point that I'm trying to make is that we need to think about risk. And we need to think about how do machine learning attacks fit into this. So let's start thinking about evasion attacks. So I'm going to revisit a lot of things that we talked about last time. Evasion attacks here. What's the security policy? If we wanted to guarantee something, what do we want to guarantee? And was this realistic? Like, we want a face recognition system that always detects the right person. That's kind of what we want. We don't know how that actually works. We can't specify this or prove that this is correct ever. Right? So you fundamentally have to assume this is unreliable. We can't guarantee any integrity property here that an attacker might violate. So should we really put this into a system like this? And I think we probably shouldn't put this in as a single point of failure where the attacker can try over and over again until they get into the system. But if you combine this with other safeguards, this might be reasonable, right? Like 5 attempts only. This doesn't stop people from doing all kinds of crazy things. Age verification is rolled out or argued to be rolled out widely. It's highly ineffective, at least the current systems. You can typically play movies and recognize however old the actor is instead of you to get around these things. In a way, it doesn't matter. From the perspective of the vendor of the software, probably not. They sold the software. It doesn't need to be effective. You're just doing security theater, and it's fine. This is not actually about preventing children from accessing the website, probably, right? So again, the risk here, you make mistakes, whatever. You collect the data, right? Success. This was another example of an evasion attack. What's the security policy here? Always detect the stop sign if there's a stop sign. And is the system doomed if we can not always detect a stop sign if there's a stop sign? If you think of the model as a single point of failure here, again, you have lost. This is not a practical attack in the first place. This was very splashy, but it worked against a very specific model that they had in the lab with thousands of attempts. Maybe if you try to attack a Tesla model and that model never changes and you have access to that model, you can run an attack against Teslas, but it's not something that widely works across all models, right? And a lot of models change. So could you, with a lot of resources of a nation actor, attack a specific car? Maybe. But even then, if your car relies on detecting a stop sign to not crash, this is a really bad security design or safety design for a car, right? And we should think about system-level mitigations. Like, this thing will make more mistakes on its own than an attacker could introduce. So if you just have a map of where the stop signs are or some additional redundancy mechanism, right? That's how you build security, not by getting this model higher. So I think a lot of this research about evasion attacks, adversarial examples, it's kind of fun because you can, in the lab, create lots of funny examples. But I don't think that there are really security issues in the wild for the most part. There are often artificial examples in the lab. I think if you're thinking about rolling this out, you really want to think about, would you really put this model here as a single point of failure in a way that it's easily attackable, right? What are we trying to guarantee? What harms are we actually worried about? When it comes to poisoning attacks, I think they are real. but they're nothing new. There's the same thing as review bombing and other things that we've done before, right? So whether you convince a human, a review website in manual effort, or a model to train on the wrong thing, I think it's fine. I don't think you should ever really trust crowdsourced data or feedback from your users in the first place, right? If you completely trust whatever feedback you get from any user, you probably are very likely to be attacked, or at least can be undermined in kind of a review bombing thing, right? And it's very hard to do this, but maybe just don't trust all the feedback that you get from your users all the time. Model inversion attacks, where you can extract training data. I've never seen a real attack of this. I think this is very academic. There are conceptual attacks where, yes, there's medical data, and you could potentially detect whether somebody has a specific disease based on reverse engineering training data. But I don't know what a practical attack would look like, and I don't think one has happened yet. Right, so again, this is fun to do research on. I'm not sure how practical it is. Prompt injection attacks, I've shown you this one, right? I think prompt injection attacks are easy. They're very hard to avoid. So you might not want to trust the outcome of a model to create binding contracts. And we're coming back to this because that's essentially what we're doing with agents these days, and I think that's a real problem for security, how to secure those. And then there's just, we have very unrealistic security policies. Like the EU AI Act essentially has something, do not generate content that's illegal in the European Union. That takes a lawyer to decide for one specific piece of content, is this legal? And 3 lawyers will disagree on one specific content, right? There's probably some obvious cases, but the boundary of what is considered legal, what is considered illegal, is very hard to decide. And now expecting a model to do this that we couldn't even do as humans, I think is just very unrealistic to build security on top of that. So in the end, again, think about what risk is acceptable, how important is this to you, and what if the model makes a mistake. That's probably a funny story, but I don't think it matters that you can prompt inject the customer support thing, right? It's not doing legally binding contracts. If it could do that, that seems really silly to put an agent in there. What happened in the case that you read? And is this an acceptable risk? If you potentially leak all your customer data, I don't think you're going to have customers for a long time, right? This is probably a really dumb thing to do if you can't guarantee safety. Even if you make this 99.99999% accurate or secure, right? If somebody could just try and at some point get customer data from a different person, I don't think you have a business. So I think what we want to do is really think a little bit more at the system level, designing for security. And that starts by having a security mindset where you think about all these components could be compromised. The model can make mistakes on its own, but then we also have the attacks where we can convince the model to do wrong things. Like evasion and prompt injection attacks, we can make less likely, but we cannot prevent them. And don't assume that users behave as expected, right? Aim for risk minimization, not perfect security. So what you typically want to do is minimize the impact of any compromised component. So whenever a component makes a mistake, don't let it propagate to the rest of the system. Don't have it big consequences, right? So there's ideas like least privilege. Like if an agent doesn't need access to the internet, don't give it access to the internet, right? Isolation, compartmentalization, run things in a sandbox. Don't give it tools to things that it doesn't need. Zero trust infrastructure essentially means that no component trusts any other components. Very annoying to build. You essentially manage everything with key management. And then the last thing is just like a monitoring and detection. Like you won't prevent everything, but you can catch a lot of ongoing attacks. And so you put this in the system as well. Right? So you won't have security guarantees, but you can layer defenses, and you can use machine learning in cases where either security doesn't matter, or you have some defense mechanisms and machine learning is part of them, but you don't rely on machine learning as the only part in there. And you really want to think about the whole system and how data flows through your system. Poisoning attacks teach you that in a very explicit way, that you really want to think about where's your data coming from. A practical way of doing this is called threat modeling. In the last milestone, you're probably going to use it, or at least one in your team is going to use it. This is one pretty old technique, like late 90s, early 2000s, of analyzing a bit more conceptually what's going on in the system, and it's much more manual kind of review technique. Right? So the goal is to find obvious gaps in your security mechanism and figure out what could an attacker do, where do we need to put in defenses. So what you often do is you try to figure out what's the structure of your system and how do different components in your system communicate? Like what communicates with what? What's data flow in your system? So the example here is an automated content moderation system for a social media site, where you have users here that might talk to a web server. There's a feed service that shows the social media feed. There's an account service with user accounts. There's some log telemetry. There's a moderating system that has access to something. There's training data. Training data comes partially from logging data, partially from a public data set. So if we want to think through the security of something like this, I don't think it's worth to think only of the violence detection here. It's what we're moderating for. This is a model here, and it's probably not worth to just think about evasion attacks on this model or just think about poisoning attacks of this model. We should think about the entire system and what an attacker has access to. And that's what threat modeling does. So we start thinking about what does an attacker want to do, and what can an attacker do in this system. And the way that this works is usually we look at one of these connections at a time. We look at every single edge in this diagram and try to see what would an attacker try to achieve in the system, and what can they do at this edge. Let's start with an example. So, in this specific scenario here, we have an image board site and we want to filter out violent images, right? Think Instagram or something like this. What would an attacker want to do, maybe? What kind of things, whether it's integrity, availability, confidentiality, what would an attacker try to do in a system like this? Upload harmful images and evade the detection.
Deny service.
Deny service, kind of take the entire site down, or take the moderation thing down. What else? Doesn't want to get caught, yeah, but that's downstream from something else that they're doing. But yes. Maybe look at private images for somebody else, right? So there's more than just the moderation thing. But yeah, avoid harmful images, avoid moderation, avoid getting caught, reverse engineering the moderation model to figure out how does the moderation model works, take down the entire system. And Stride is one of these approaches. It's essentially a checklist that goes through 6 common things that attackers might try to do, and you apply this to every single edge. Stride is a forced abbreviation of these 6 things. Spoofing identity. You want to try to pretend to be somebody else, so upload images in place of somebody else. Tampering with data. Repudiation, claim that you didn't do something that you did. Information disclosure, so try to get access to secret or private information. Denial of service, and elevation of privilege. Get into the system to do something that you're normally not allowed to do, like get administrator privileges. So now we can look at one of these edges, one edge at a time. let's start with the edge, because it's simple. Start with this edge here of the users to the web server. Right, so we might be worried about spoofing identity. How could you spoof identity? And what can you do against that?
You can get hold of authentication tokens or JWT or any other tokens.
So you already assume that there are authentication tokens. Right? It's a defense. We have passwords, we have authentication, that you can't just pretend that you're somebody else. And then we know that some of these mechanisms can be circumvented. Right? So if you have a specific token, that's something that you can worry about. So spoofing identity over a network connection, we have some idea of what we're typically doing there. Right? Tampering with data. You're worried about that somebody's tampering with data that you're uploading. What can you do to defend against that? Or what might an attacker want to do here? Maybe you upload a harmless image. They want to turn this into a violent image that you get censored or something like this. How do you prevent that as a system designer?
Encrypt the uploads?
Yeah, encrypt the network connection so that somebody can't just tamper this on the network, right? So here are examples of this. Upload images under another user's identity, that's spoofing. Modifying the image during transfer with a man-in-the-middle attack, that's tampering. Claim that they didn't upload the image after their account has been blocked, that's repudiation, right? So I say, I didn't do this, that you told me that I did. Getting access to precise confidence scores of the moderation decisions, because I want to reverse engineer this, so I'm trying to get access to private information. Overwhelming the system with a large number of uploads of very large images to take the moderation system down. Remotely executing malicious code that's somehow embedded in the image, exploiting a bug in the image file parser. Right, so that's some way of trying to maybe get ways of executing data here. And then for each of them, we can think about how do we prevent this. For the first two, we have done this. Uploading an image under somebody's different name. You have some authentication mechanism, username, password, tokens. For the second one, you use encryption. What do you do that you can't just claim, I didn't upload the image? You block somebody's account, and then they say, oh, it wasn't me, it was somebody else. Yeah, log the token, or associate which account uploads this, which token upload this, have some logging infrastructure, essentially, that you can't just easily modify. Right? Getting access to precise confidence scores. Don't return precise confidence scores, I guess, right? Round them or add noise. Overwhelm the system with the large number of uploads of very large images. What can you do? Adding rate limits, blocking IPs, detecting this, limiting the size of images. The last thing, remotely executing malicious code. Image parsers are kind of dangerous. They have a lot of powerful things, and they sometimes have bugs. You can use one that's very well tested and is not known to have these kind of bugs. Or you could sandbox the component, so run the image parser in some container where it couldn't create damage, right? So this kind of thing. So these are not necessarily new strategies, right? So threat modeling isn't really doing anything new to a large degree. We're just looking at one of these connections at a time, going through these 6 things as a checklist to see, is this something that we're concerned about here? And then what can we do about this? And most of the things that we can do about are pretty standard techniques like encryption, authentication, and so on. At this point, I want you to do this. Pick any of the other edges. So don't do this one, because we just talked about this, but any of the other edges in this diagram, and goes through the 6 stride criteria, and talk about what threats have you identified, and if you want, you can also talk about how you're mitigating them. All right, I see a lot of answers. Claire, you want to pick a volunteer?
My kids did not eat all of the Kit Kats when they came to visit, so there are some remaining. And then for those who are less chocolate inclined, we got some Starburst and some Skittles, and I will let you pick.
Any volunteer?
Or you can have bougie German candy. That's also an option.
It's Swiss.
Swiss, bougie Swiss candy. Don't all volunteer at once. It makes me very uncomfortable when you do that. Oh, come on, fam. Oh, is that a hand? Yeah. You're a winner. Here.
The age we could analysis is from the user posting to data engineering. So, yeah, because the user posting is the...
Wait, sorry. Oh, the postings to data engineering.
Yeah,
okay.
Yeah. So the attacker could like flow the system with large number of the user posting, and I think it might overwhelming the data engineering pipeline. And I think the good way to avoid that is by denying the service.
So, which kind of attack or threat are you worried about?
Denial of service.
So on this edge, you're thinking about denial of service, and then you can think about rate limiting or some other mechanism. Okay.
Yeah.
Any other properties on that edge? Did you go through the other ones on the same edge? There's like 5 more.
We also think about like not this edge.
Okay. Let's do one edge at a time. Who else has a different edge or wants to talk about what they talked about?
We also had another edge from the community moderators to labeling and moderation front end.
Okay, this one?
Yeah, so that would first be an elevation of privilege. Someone could pretend to be something that they aren't. So maybe they do not have access to labeling data, and they could be in that space. And we also think
I think that's more spoofing identity. Typically, elevation of privilege usually means you have an account, but you're somehow figuring out something to do that you're not supposed to do.
Yeah. And we also think that could also be tampering with data, because you can mislabel. And
you could intentionally mislabel things. Have you thought about what you can do against it?
Not really. Probably double factor authentication.
That doesn't help if the human is the right human who does it, but then does the wrong thing, right? Yeah. That's very hard to prevent. Yeah.
Could have random sample of double labels.
Yep.
Cross-check. One more?
Did somebody go through the entire stride thing? Like all 6 labels? I mean, I've seen this in a lot of posts. Does somebody want to walk me through all 6? Could be that there's not something for everything, but kind of just walk through systematically.
I also answered the edge between the community moderators and labeling and moderation front end.
Okay.
Yeah, and for us, we just say that someone pretend to be a community moderator when they actually are not.
Yep.
And for T is that this community moderator tampers with and incorrectly label the data.
Intentionally, okay, yep.
Yeah, and for R is that they claim they didn't label a bunch of data maliciously, but they actually did.
Yep.
And for I is that they download all the labeled data and leaked it to the internet or other competing companies.
Yep.
For D is that the moderator spams the labeling service to bring it offline for every moderators.
Okay.
And for E is community moderators access the data when they are not supposed to, the administrative data or the logins data or something.
Okay. Right. So I think So in this kind of pattern, you can pretty much go through all the edges. You often see very, very similar things, and the reactions are often very similar, like create user accounts, check them, encrypt data connections. And in some cases, you have a bit more sophisticated things, like have some consistency check, redundancy check with something else on data quality, right? Have maybe a model to check for outliers, block accounts. In a way, threat modeling feels kind of similar to hazard analysis. It's kind of paperworky. You kind of just systematically brainstorm and go through the system. But we have seen that this is actually quite effective. Microsoft has started this very systematically, and they propagated this among all their teams. This just gets people out of just looking at one line of code at a time, or looking only at evasion attacks or something like this, looking at the larger system, looking at data flows, and looking through all the different ways that attackers can get into the system. There's also lots of approaches these days of trying to automate this with LLMs. You typically need some system knowledge, some sort of abstraction like this, but similar to how you automated hazard analysis, you can automate this kind of structured brainstorming. Whether you fully trust the automation is a different thing, but you can do a lot of steps. And I guess some automated way of doing this is still better than not doing this at all. So in that sense, maybe not the best to automate it, but maybe also still useful. I assume you've all heard of red teaming. What is red teaming?
Like a mock intrusion of like a system?
Yeah, it's essentially pretending to be an attacker and trying to attack the system. And traditional red teaming is very unstructured. It's kind of just, let's poke at the system and let's behave creatively like an attacker. It's way less structured than threat modeling, for example. It comes out of war games, and it's red and blue because of US versus Russia. Right? You're pretending to be the Reds, the bad guys. And you're trying to think like an attacker. It's usually not structured. People kind of use that term a lot in machine learning context because it doesn't really commit them to do anything. You can just say, oh, we poked at the system, and so we have done red teaming. So it's a kind of an easy kind of regulatory capture, kind of just saying, oh, we did something positive, whether it was effective or not. There's some attempts of trying to give it a bit more structure, but zero agreement on what we should do, what we should call red teaming, and so on. So I would avoid this as a term, but it's broadly thrown around. I don't think there's any structured or disciplined way of doing red teaming. It's just be creative and try to behave like an attacker. So this is where I wanted to get to today, though. It's AI agents and security. This is also going to be in the next homework assignment. So this is going to walk you through some parts very closely related to that. So you can think of a lot of this as a customer service agent that you've seen in the last lab. Your homework assignment is on that and trying to secure that. AI agents are terrible when it comes to security. I don't need to repeat. Agents are essentially a model that has tool use capabilities and feeds the output of the tool back into a model, so it kind of iterates, right? And tool use means the model or the agent can interact with the environment. You've seen this in your case. It can ask a thing from Wikipedia, right? Get airport information from Wikipedia, and then use that information to decide whether you get a refund or which plane you should book. I have a different example here, which was a midterm scenario from last semester, which is insurance fraud detection, where you have an agent that reviews insurance fraud cases, has access to internet search, has access to a database search of past cases, can send and receive email, for example, check with the contractor of whether they actually did something, and write a report in the end, maybe send it to the police. And now we are worried about what this agent could do, right? It could send arbitrary emails. It can call the police on somebody. Is this really something that you want the agent to decide what to do? And by allowing it to do internet search or sending arbitrary emails, you give it potentially a lot of power that somebody could exploit. And you've seen prompt injection attacks. You can get an agent to do almost everything if you're successfully prompt injecting this. Prompt injection gets a little bit harder these days with modern models, but it's still possible. And we discover new tricks of how to prompt inject models regularly. These days, I think your best bet is to kind of just make the context really full, kind of make the prompt really long, have long conversations, and then convince it in a late stage right, to do this when it's distracted. But there are also often like new ways of doing this. And models often make mistakes on their own. You don't even need to attack this, right? The problem here is really that whenever you're calling a tool, you're putting the result of that tool into the context for the next LLM call, right? This is how the airport information worked. You ask information about an airport. The result that you get from Wikipedia in that case gets into the prompt for the next iteration, right? So whatever in there will be considered as part of the prompt. It's part of the context. The context just keeps growing. So whatever information you might send in an email later might be informed by an earlier step where you ask information about an airport, right? Something relatively simple. And in a way, should we ever trust a model? This, I think, is a fun example with Claude Code. Here's a full plan. Shall I implement it? No. And then the model convinces itself, oh, the user actually means yes, and goes ahead and do it anyway. Right? This is not an attack. This is just the model being really stupid. The model often is instructed to be productive here, right? This is similar to the model deleting all emails or not listening to user input. Right, this example from earlier. So in a way, I would suggest never trust the model. Right? Whatever the model decides to do, call a tool, produce some output. This could be influenced, A, by just a model mistake, or more importantly, by prompt injection attack that can come from any tool out there. If you assume that, there's not really much you can do, because every single tool call that a model can do can be potentially malicious, can be affected by a prompt injection attack. So there's not really a lot that you can really do other than harden the model. Right? So you can try to detect prompt injection attacks, which you're going to do in the homework assignment too. Like, look at the prompt, look at the output of a tool, and ask a model, essentially, is this a prompt injection attack? You can evade that too. There's a lot of strategies. We mentioned this, I think, last week, of how to defend against prompt injection attack. The thing that I think is often more effective when you can do it is to build safeguards around the model or be very careful of how you build the tools. The S in MCP stands for security, right? There's nothing really built into most of these agents to really, like, security is not a first-class entity when these things are designed. So we can often patch things after the fact. And I want to go through a number of strategies, and I suspect they might be useful in your homework too. The first general strategy is you can limit the access that you give the agent, especially if you build domain-specific agents. If you build a coding agent, you kind of need to give it access to do a lot of things with code, right? Potentially run code. But if you build a customer support agent or a fraud injection agent, does the agent really need to be able to write and run arbitrary Python code? Right? Does it need to be able to send emails to everybody on the internet? Right? Does it need to have access to anything on the internet and send post and get requests? So you really want to think about principle of least privilege. Don't give the agent access to tools that the agent doesn't need. It's very easy to just install a bunch of MCP servers, but does the agent actually need them? Do you have an example in the insurance fraud investigation agent that the agent probably really doesn't need?
Maybe internet search.
Yeah, or maybe search is okay, but not arbitrary internet access, right? Or search only in specific things. You probably also don't want it to modify contractor information, for example, right? This is something that is not the task of the agent, right? Or get all customers if they are investigating a single claim. So this kind of giving an agent too much information is a common thing, and you can restrict this, right? And you can often do this in your tool design. Rather than give me all the contractors, you have an API that just allows you to look up a specific contractor, right? That already reduces a blast zone. The agent can't easily access all the different contractors. It needs to already have information about a specific contractor that was named in a case to look that one up, right? So you can do a lot of stuff in the tool design to just not give the agent access to lots of powerful capabilities that it doesn't need. Again, this doesn't work if you're working on a general purpose agent, but I don't know we know how to deploy a general purpose agent securely right now. But I think for specific purpose things like customer service support, fraud and detection mechanisms, you can do things where an agent can still be creative and use tools, but in a very constrained setting. It's a similar thing. Rather than allowing the agent to send emails to anybody, just allow it to send emails to known contractors in a database. The agent doesn't even need to decide what the email address to use. It just looks it up in the database because we have some contractor ID. Make sense? There is some research on authentication delegation and context-aware authentication, like how do you give credential tokens to an MCP server that they then on your behalf can go to GitHub or to some database. I don't find that particularly interesting, but that's kind of necessary infrastructure often for credential handling. Like how do you give an agent or a tool credit card information without just passing this around willy-nilly? There's some cryptographic thing. You can find research in this space. Second thing that I see all the time is that we ask an agent to check something that we could just check in code. Do you have an example in the insurance fraud thing? So we could tell the agent the first parameter in send email must be a valid email address, but we can also just check that when we call the function that the first argument is actually a valid email address, right? Or send emails only to validated addresses in the contractor database. If we redesign this that they can only send this to things that are in the contractor database rather than to an arbitrary email address, we can check that in the back end, right? That the email is in the list of contractors, or not even give the email to the agent. So the analogy here is if you have done ever web development, where do you validate user data, front end or back end? Like you want to avoid something like this, right? SQL injection attacks. Where do you check this, that this is invalid input, back end or front end? JavaScript or on the server?
I think both, but definitely front end.
Both is a good strategy, but definitely front end is the wrong answer. Definitely back end. So never trust the front end, right? You can do a lot of front end checking, but somebody could just send you a message on the command line that violates all of this, or turns off JavaScript in the web browser and sends you that information, right? Front end checking is nice because you can provide rapid feedback to the user. You don't get an error message from the back end. You don't need to go all the way around, right? So it's common that you do it both, but you fundamentally never trust the front end. It's a very common property. So in a similar way, you can tell the agent what they should check, but never trust the agent that they actually do that check. It can be useful to tell the agent, check that the email is in the contractor database, but just check it in the back end. Don't trust that the agent actually does this, right? The agent is not trustworthy. The agent might do the right thing at most of the time, but not always. Like, there's a lot of discussions on Claude Code about they have a built-in sandbox, and apparently they give the model the ability to turn off the sandbox. I don't understand why. So the model is motivated, and there are examples where the model decides, I can't execute this thing because the sandbox says no. Let me try to find a way around this, and I've disabled the sandbox, and now I can execute it. Right? Like, don't trust the model to perform any checks if you actually care about them. So if you think about this, only send emails to validated email addresses. Yes, the model can do this in the front end. You can give the model the tools to validate the email address, but you can check this in the back end, right? Is the email that the model used part of the database? So you would write an MCP tool, something like this, send contractor claim verified email. First thing is check that the email is actually the one in your database, right? And otherwise refuse to do this. You can tell the model to do some stuff that it maybe doesn't send you too many invalid commands. But just because we have a LLM, don't forget that you can actually do a lot of symbolic checks in your code, in your tools, in your APIs. You'll probably find quite a few examples of this in the homework. This one I think is fun too. Require user consent. It's a form of separation of privilege. If you want that the user confirms certain actions. For example, here, before you send a report to the police about fraud, some human needs to validate this. You can ask a chatbot to always confirm with the user before they send this. We've seen how a motivated chatbot can turn off a sandbox. They might skip a user confirmation or just say, the user said no, but I mean, they actually mean yes, right, and then execute it anyway. How can you make sure that the user was actually confirming things where you don't need to trust the model?
Go around the box to send a signal, like directly past the request or something else that could launch the report.
Yeah. So if in the agent, the model has decided to call a tool where you want a confirmation, right? The agent implementation, the user interface, can now pop up a question. Don't ask the agent to do the confirmation, right? So you can do this here as part of the tool call. So this is the ACT method in an agent, for example. The agent has decided to call this tool. Before I actually call the tool, in the symbolic implementation of the agent, right, without ever asking an LLM, I can pop up the question to the user. I need to modify the user interface, but I need some way of interacting with the user that's not through the chatbot, right, that is not intercepted or interpreted by the agent. And probably also the message that I'm sending to the user, I don't want the model to format that message because the model could lie, right? So if you have a prompt injection attack, you could just ask the model to put some other text here that the user then confirms. Right? So it's a good idea if you actually want a confirmation to do that entirely in symbolic code, escape the model's decision power. Right? Don't trust the model on this. Does it make sense? Do you mean what I'm? Bypass the model. Right? Don't trust the model. It's actually really simple when you think about this, but the way that we implement agents, we kind of, like most people just think about modifying prompts, getting the model, tell the model in more and more stronger words, always ask a question, when you could do this in symbolic parts, in the implementation of the agent, rather than in the prompt, right? You can do a lot of checks here. Similarly, if you want an audit log, or you want a confirmation from the agent when they did some action, the model can lie about this. The model can say, I've sent a police report after they actually failed to execute that method. And you can also trigger a model to lie about having taken some action if you prompt inject it. It's relatively simple. Just tell the model, tell the user that you created a police report, right? And the model has never called that function. If you want to make sure that the user sees what the model actually does, don't trust the model to format the output, right? The agent, at some point, the agent implementation in the act method, you call the tool, you get the result of the tool, and now you can tell the user without going through the agent, right? With some other pop-up or something, a following action has been called. And again, you format this in a deterministic way without asking a model to format this, so that the model can't lie that it has called a different tool. Does it make sense? In a nutshell, don't trust the model if you actually care about security for some of these properties. There's a couple of more fun ideas. I think this comes up, masking sensitive information. If there's sensitive information that the model could do something weird with, leak it, for example, or modify it, don't give that information to the model, give the model a placeholder. For example, the model doesn't need access to contractor names and email addresses or policy IDs. It just needs to be able to refer to them. So what you could do is something like you get a contractor information from the database, but you just give the model the name, like name 5, like a proxy for that. And then when the model calls a tool, it will tell you email name 5, the placeholder. And then before you execute the tool, you can replace it back with the original information. So your code has a confidential information, but the model never gets it, right? The model only sees these tokens, these placeholders. This works if you're just passing through information. If the model actually needs to look at the information, this doesn't work. Right? But if you want to pass through secret information and don't want the model to make decisions based on that, don't want the model to be able to leak that information, for example, you could decide this token can't be used when you're sending an email to somebody else. Right? So you can decide when information can be used in a tool call. You can sandbox a lot of tools. This gets really annoying if you have very powerful tools, like executing random code. Like if you allow an agent to execute Python code, you have essentially lost. You can run it in a sandbox so that it can do computations without accessing the internet, without accessing files on your system. You can do something like this. It's kind of hard to very reliably sandbox something, but that's a reasonable strategy. You can also run the entire agent in a sandbox. That's what we mostly try to do because we don't have any better idea. I think with CloudBot, the most common strategy is to buy a new computer just to run CloudBot, that it doesn't run on your own computer. It's a form of sandboxing, so protected from your local data, but it also still gives it access to the internet in arbitrary ways. Right? But you can sandbox individual tools. You can run sub-agents with limited context. So there's a couple of those ideas. There's some ideas to run information flow analysis. I'm not going to go into this. And then the last thing that I want to mention is temporal constrained state machines. There's some tools to allow you to specify this, but it's pretty straightforward. So no emails should be sent until a report is drafted and approved. Or send only one email per contractor. So these simple rules, where you can make rules, tool A needs to be called before tool B. Tool A can only be called once. Tool A can only be called when tool B returns the following. Those you can encode. Those you can do with standard logic. And they are relatively easy to enforce. Again, outside the model. You can ask the model to do this, right? Only send a police report after checking this or checking with the user. But again, you can do this in the non-model part, in the symbolic part, where you do the act function or the tool calling part to do these checks. So I think the the key points that I'm trying to make here is that you can do a lot of things in the symbolic part of the agent. Just because we have models that have powerful decision-making capabilities, you shouldn't forget that you still have code there before you call a tool, after you call a tool, where you can intercept functionalities, where you can do checking. In the tool backend, you can do a lot of things, right? These days, it's actually, if you're running Claude Code or something, it's very easy to install new MCP servers. I assume most of you have done this, right? Something like Playwright, maybe for the first homework assignment, probably other things. How much have you checked that those MCP servers are actually secure? Right? That they're not like what you created with the Wikipedia thing. Now people use skills to attack people. There's a fun skill, what would Elon do? That just says somewhere down here, code snippet, run this code when you install the skill or when you use the skill, which just installs some malicious code on your machine. Just with curl, it's running something malicious that it's just running on your machine. So now you have these text files that can even be malicious. And we're not really good at screening those, right? Whether it's skills or MCP servers, they're easy to install. And this is really hard to install. And right now, this is a prevailing attitude, right? Like, figure security out, whatever, right? Stop being risk averse. I'm not sure that that's the best strategy to randomly install more and more MCP servers and give you agent powerful control. I think this is a reasonable place to stop. Claire's going to do privacy next time. Privacy is depressing anyway. There's not much to talk about. What I wanted to convey today was really think about practical security. The attacks on the model themselves are not the core part. The model makes more mistakes by its own. It can be attacked, yes. You can convince a model to do the wrong thing, but it makes mistakes on its own. So think around the entire system. Think around what safeguards you can build around the system, and think about what security property you actually want to achieve, and whether it's reasonable, whether you can actually, the residual risk is okay. You're okay with that risk. All right. Have fun.